been making videos on network theorems, specifically problems related to network theorems, how to solve networks or analyze networks based on several theorems. In all these videos, I have not explained the theorems in detail. However, I presume that the students have sufficient background to understand these problems. However, in most of the videos, I give a little bit of side note which is required to understand the video. This problem is about maximum power transfer theorem, which happens to be one of the important theorems in network analysis. I have done videos on superposition theorem, Thevenin's theorem and Norton theorem. Now, in the series of problems on theorems, I have taken up this particular problem, which is about maximum power transfer theorem. If we read the problem, he says, determine the load impedance to be connected between A and B such that it absorbs maximum power, and find the maximum power absorbed by the load. Use the following network. Okay. So he wants us to calculate, he wants us to find out the impedance which is capable of absorbing maximum power from the source. So what is the value of that impedance? How do we arrive at that impedance? That is the question, right? So in order to do this problem, we need to have an understanding of maximum power transfer theorem, which is a side note I just want to give here at this point in time, so that this problem makes sense to the viewers. If we have a network like this, that means a source is available to me, which has an impedance. It's a voltage source. I'm just writing the voltage source equivalent. I can even write a current source equivalent. However, this is the source I have with V as the voltage of the source. Let me say that the source has got an impedance, ZS, which may in rectangular form is represented as RS plus JXS. I have this source. This source is has got terminals A and B. Suppose I connect a load here across A and B, and I am capable of varying this load. Let me presume that I am capable of varying this load. This ZL, again I presume the rectangular coordinates of this particular load as, let us say, RL plus JXL. Okay, so this is the arrangement I have. I am able to vary ZL, and there is a source. Where is the source? Source is on the side of the network. On the side of this network, we have the source. On the left side of AB, we have the source. This side, we have the load. Okay. So, if we want maximum power to be dissipated in the load, in this load, if you want the maximum power to be dissipated, what should be the value of this is the question. So, what should be the value of ZL? ZL should be what? Such that it absorbs maximum power, or it is capable of drawing maximum power from the source. According to maximum power transfer theorem, it can be proved that if ZL is made equal to the complex conjugate of the source impedance, I'll repeat, if the load impedance is made equal to the complex conjugate of the source impedance, then maximum power absorption is possible in the load, or then maximum power takes place in the load. So we can prove this by simple fundamental, theory of maxima minima. One can always prove this. How this is possible? Okay, what do we mean by the complex conjugate of source impedance? We know that the source impedance is RS plus JXS. The complex conjugate obviously would be RS minus JXS. If ZL is made equal to the complex conjugate of the source impedance, maximum power is possible. That is what is the theorem. And the maximum power that can be absorbed in the load can be given by V square divided by 4RL. And these things can be deduced. It's not a thing that has to be remembered. One can always, you need not accept blindly. One can always, deduce these results. So this is what it is. The load impedance should be equal to the complex conjugate of the source, and the maximum power that gets dissipated in the load under these conditions is V square divided by 4Rn. This information is sufficient for us to understand this problem. Okay, so now we will go ahead with the problem. I'll clear this portion which I have written. Okay, I will mark it and erase it. That would be in one stroke I can do it. I'll cut. Okay, now this is the problem before us. Determine the load impedance to be connected between A and B such that it absorbs maximum power. The question is, what impedance when connected between A and B will absorb maximum power? So we know, according to maximum power transfer theorem, the load impedance has to be complex conjugate of source impedance. Alright, now what is the source impedance? We have a network which is connected in a particular manner. Right, so you have two parallel impedances here, you have two parallel impedances that is in series with another reactance, and you have one resistance here, there is a branch on this side, there is one resistance on this side. So how can you see this entire network as one resistance? If we pay little attention, if we can relate this with the Thevenin's theorem, we are able to see that this entire network can be transformed into a simple voltage source. Right? You can convert this into a simple voltage source or a current source. If we apply Thevenin's, you will get a voltage source. If you apply Norton's theorem, you will get a current source. So if we can convert this into an equivalent voltage source, we will get one voltage magnitude and one series impedance. That can be treated as a source. Then we can contemplate what is the load impedance which will give us maximum power. From the theorem, it has to be the complex conjugate. So the first objective is to convert this network into a Thevenin's network. Or it is essential for us to convert the given network between A and B into a Thevenin's equivalent. That is why Thevenin's network is so very important. So what's our first step? So our first step would be, I will try to take the, I'll see if it is possible to scribble here. Step 1. Okay, that one is gone. Okay. To find, what's wrong? I don't know what went wrong with this. To I don't know why such a thing happens in between. This is not working. This color I am not able to pick for some reason. What do I do? I'll sometimes, these things pose a lot of problem to me. Okay, let me write only. Step 1. To find the first part we will do. We will not find the open circuit voltage. We will first find out what is the load, what is the source impedance, okay? To find the ZTH, Thevenin's equivalent impedance, we will try to find this. How do we find the Thevenin's equivalent impedance? It is simple. We deactivate all the sources, or in other words, we switch off the sources and then try to view the network between the terminals under consideration and see how it appears. All right. So we can do this network. To do this, we need to rewrite this network. I will pick up the network. I'll copy the network. I'll paste the network. Okay. So we will try to view it between A and B. Okay. The network, we will try to view it between A and B after we deactivate the voltage source. What do we mean by deactivation of the source? This voltage source should give zero magnitude of voltage. So that is possible when you replace these 2 points across which you had the source by a short circuit. Okay. Now we try to view the network between these 2 points. This is how we are going to view. Okay, so we can simplify a few things. We can see what is the equivalent of these things. We can have it into one. These 2 are in parallel. That will be in series with this, and that will come in parallel with this, and that will be in series with this. So I suppose it's easy as to how this is seen. Okay, this J5 and J4 parallel, what is that equal to? So J5 parallel J4, this impedance, what will this be equal to? It is the product J5 into J4, product divided by sum, rather that is minus rather, okay. So minus J4, right? So this is J5 minus J4, okay. This is going to be minus J square 20, I'm going little slow. This is J1, all right, minus J square into 20 upon J1. So J square again is minus 1. That will be because J, what is J? J equal to under root minus 1. J square obviously is minus 1. Okay, so this is going to be simply 20 divided by J1. So I will rationalize this by multiplying and dividing by J1. What I get is, again I'm getting J square in the denominator. This is J20 divided by J square, or it is minus J20. Okay, that is what it is. So if I can parallel J5 and minus J4, this is minus J4. Okay, the parallel of these 2 is my minus J20. Okay, so that what I mean is I can replace this by minus J20. So this whole thing is now equal to, this is equal to minus J20. So we can see this minus J20 comes in series with J20, and that comes in series with 10. How do I say so? It is, we try to view the network in this direction. So what we mean is we imagine a source between A and B. We imagine, let us presume that the current enters A. I am assuming a DC source only, like, some current, like instantaneous current. Okay, instantaneous current enters this node. Okay, so it has to split into 2 parts, one this way, another this way. So this entire thing and this 10 ohm, that will be in parallel. Okay, now, and that will come in series with 7. But this entire thing, if you can see, the current that enters this combination will flow through this 20, J20, will also flow through this 10. So this minus J20 is in series with just J20 is in series with 10 ohm. Because all the 3 are carrying the same current. That is the logic. Alright, so all the 3 things gets added up. This J20 minus J20 would add up to 0, and this is 10 ohm. So now 10 ohm and 10 ohm in parallel. I suppose you can see. Now the network becomes something like this. Okay, this is in yellow, doesn't matter. This is 10 ohm. Now this is 10 ohm. And this is 7 ohm. This is how my network has got itself reduced to. Okay, this is 10 ohm, 10 ohm. This is 7 ohm. This is A and B. What happened to the reactances? It got cancelled. If we can see, this gets cancelled with the other one. I'll take this color. This J20 got cancelled with minus J20 because they're in series. Alright, so only 10 remained. 10, 10 and 7. So this is 10, 10 and 7. 10 and 10 in parallel. Equal values, 2 resistances of equal values in parallel will result in half the 2. 10 into 10 divided by 10 plus 2. Or this is equal to, if I view the network this way, now this RTH, the Thevenin's equivalent resistance, it has come out to be resistance. You can even call it impedance. This is equal to 5 plus 7. How did I get 5? It is 10 parallel 10. If that has to be written, that can also be written. This is 10 into 10 divided by 10 plus 10 That becomes 5 plus 7. So in other words, the ZTH or RTH, okay, in general you can call it ZTH, this is equal to 12 ohms. This is an important inference we have. So my load source resistance is simply 12 ohm. Okay. Now this is simply 12 ohm. So my load has to be 12 ohm, right? For maximum power transfer, because it doesn't have any reactive part. No imaginary part. If there is imaginary part, then we could have thought of conjugate. Now there is no question of conjugate here in this case. Okay, so we are able to infer that the load resistance has to be equal to the source impedance equal to 12 ohms. Okay, so load impedance should be equal to the source impedance which is simply 12 ohms. Okay, so we are able to do one part. Now he says, what is that maximum power? If this is the impedance you want to connect, what will be the maximum power? So in order to do that, you need to know the voltage of the source. Now comes the second part, like what is the Thevenin's voltage? So we need to find out what is the open circuit voltage. So step is to find VTH. Why do we want to know VTH? Because we need to see the entire network as a voltage source. Okay, so to find VTH, what we do is we try to take the network, find out the open circuit voltage. Okay, so I will rewrite this network. I will take this network. I think this network will do, because this is the resultant network. Okay, I'll take this part first. I'll copy this portion. Okay, I will paste it here. Okay, I pasted the network. Now this is equal to, this network is equal to, this is equal to a situation like this. How? A resistance of 10 ohm and another resistance of 10 ohm. You have a source here. Rather, I will remove this. I will write this to be 10 ohm. This also has to be removed. You have to have a source. What is the magnitude of the source? It's 100 ohm, 100 volt, right? The source is given to be 100 at an angle 0. This is my source V plus. All right. So this is my V, which is this is my V, which is equal to 100 volt. This is 10 ohm. This again is 10 ohm. And I have one more 7 ohm here, that also I'll put. A and B. Okay. So whatever voltage that gets developed here is my VTH. Open circuit voltage. We have opened A and B terminals. It is open only in the problem. If there was any connection, we need to remove that. Create an open circuit, find out this voltage. Okay, how do we now find out VTH? It is a simple voltage division rule. It's voltage division. How will the current flow be? If we look at this network, it has been converted into a simple resistive network. Okay, the current flow would be now from the source, it will only circulate here. There won't be any current through 7 ohms. Here there is no current. This is zero current. Because current doesn't have any return to come back. you have an open path between A and B. So there is no current there. That has to be clearly appreciated. Okay, now with this idea, we will try to find out what is the voltage across 10 ohm. That itself will appear as VTH, right? So voltage would divide between one 10 ohm and another 10 ohm. It is like whatever current that flows through, the current would be like this. Whatever current flows through this 10 also flows through this 10. 10 and 10 are in series, right? 100 divided by 20, that is 5 ampere current. 5 into 10, that will be the voltage. That one way of doing it. Other way of doing it is voltage division between two equal values of resistances. So it's 100 volt across 10 and 10, so 50 across each one. So whichever way you do, whether you do it by simple, what do you say, common sense, or elaborately you want to follow something, you will simply see that VTH is equal to 50 volt. Okay, is that clear? I suppose it is clear. VTH, if you want to elaborately calculate, you find out what is the current. Current is 100 divided by 20, that is 5 ampere. 5 ampere would flow through 10 ohms. 5 into 10 is 50. No current through 7. How do we exactly calculate the potential difference VTH or open circuit voltage? We go from A to B along any path. What is the potential drop across 7? There is no current. 7 into 0. This is 0. This is 10 into 5. 50. Come back to B. Whichever way you go, you will get the same value. Okay, so open circuit voltage or the Thevenin's voltage is 50 volts. So what is it we are trying to now infer? The given network, this given network, I will take the network, main network only I will take. I will copy the original network. I'll copy the network. I'll put it here. Rather, I'll put it little farther. Okay, now this network reduces to a Thevenin source. What is a Thevenin source? It will have a voltage. Then it will have an impedance. This is my Thevenin source. So any network between a pair of terminals can be seen as a Thevenin source. This is my terminal A, terminal B. This is my ZTH, whose value is 12 volt. And this is my source, which is VTH equal to 50 volt. Okay, now I'm planning to connect a load. Now what I am doing is, I'm connecting a load here. This is my ZL. So according to maximum power transfer theorem, ZL equal to ZTH or ZS. This is equal to 12 ohm. Right? I have to be careful with the units. 12 ohm. Equal to 12 ohm. Okay, for maximum power transfer. Maximum power transfer. And what is that maximum power? Pmax, if you want to compute the value, how much power gets dissipated in the load. If at all I'm interested in that, I may have to do Pmax equal to V square divided by 4RL. Only the resistive part of the load has to be taken because that is the one which consumes the power, right? So my load impedance is now into, this is 12. Okay, so I need to compute this and I will get the result. 50 divided by 12 into 4. I mean 50 square. How much will that be equal to? I perhaps would be needing a calculator. Let me see and give you the result. This is 50 square divided by 4 into 12. That will be, this is equal to 52.08. So many watts. That completes the problem. Okay. That completes the problem. If you connect 12 ohm resistance between A and B, you will be able to get maximum power. Okay, so hence the utility of this theorem. So this much power gets absorbed in the load. When you connect 12 ohm resistance between A and B, you can get maximum power dissipated in the load. Any other value would not yield maximum power. Okay, this is an important, interesting theorem. So where efficiency is not of much concern to us, we try to go in for matching the load with the source. Because efficiency here is 50%. 50% efficiency is there. Because half is in the source and half is in the load. It may not be possible. It may not be very useful. This matching may not be very useful when we are trying to concentrate on the efficiency. Okay, this is to be borne in mind. Okay, this is an important theorem, a simple problem I've taken up. I can make a couple of more videos on this before I move on to the next article in network analysis. I have otherwise covered up some problems on mesh analysis, some problems on nodal analysis, and I've taken up theorems. I'm focusing on problem solving techniques than on the theoretical concepts. So one can always read books for theoretical concepts, and wherever needed, I'm giving trivia. I suppose I will stop this video. Thanks for your viewership. If you can post some questions, I would be very happy to attend. Anyway, thanks.